Hey guys, hope you're all doing good. In this video, we are going to be getting started with turbulence modeling, especially in CONVERGE CFD. So first of all, what is turbulence? Turbulence is a state of chaotic and unstable fluid flow, as I'm showing here. And it is basically the opposite of laminar flow, right? This is something that you might have already studied in your undergraduate textbook. Now, with respect to IC engines, you have something called as turbulent length scales, right? At this point, I'm not going to be explaining what this is. If you refer to a standard textbook on turbulence, you should be able to figure out what length scales mean. And with respect to IC engines, the length scales ranges from 0.1 to 1 millimeter. So these are really small values. And resolving these length scales are very important for obtaining physically meaningful results. And in the next slide, we will basically see what that actually means. So what does physically meaningful results even mean? For example, let us say a combustion occurs. Say that it's a pre-mixed case and you have a spark plug as your ignition source. So what happens is during combustion, your turbulence, right, corrugates and stretches the flame surface area, right? And because of this, you get faster burning. And sometimes you also get flame extinction, which occurs because of overstretching of the flame surface. Now, these are physical phenomena that actually happen when turbulence exists. And if your CFD code is not able to capture these effects, then you're predicting your burning process incorrectly, which means your performance data and your emissions data might be completely off. So how do we characterize turbulence? Well, Reynolds number, right? So Reynolds number is the ratio of your inertia forces to the viscous forces. Typically, depending on the Reynolds number, you can say if the flow is laminar or turbulent, or if it's in the transition region. So for example, if you take a simple round pipe, you might have studied that if the Reynolds number is less than 2300, it's laminar, above 4000, it's turbulent, and in between, the flow is said to be transitioning. Now, with respect to IC engines or say gas turbines, the flow is always going to be turbulent, right, because of the really high velocities that are involved. So with respect to IC engines, let us say that we have a non-premixed engine. So non-premixed engine is one where you actually have a fuel spray. So if you take a diesel engine, then you would say that that is an example for a non-premixed engine. In a diesel engine, the combustion, right, the rate at which combustion takes place depends on how well fuel and air are mixing, right? So this is why you call it as a mixing controlled combustion process. And turbulence increases the rate of mixing. Okay, so this is something that has been well observed. However, if you have to capture this computationally, your cells, your computational cells should be on the order of 1 micron, which is really, really small. Now, if you take a look at premixed engines, like I said, turbulence wrinkles the flame front and it also stretches the flame surface area. You still need cells of the size of 10 microns to accurately capture this behavior. Now, obviously, running a computational simulation with these type of measures is prohibitive at this stage. If you run a simulation with this type of a mesh, it's going to be accurate, but it's going to take forever to run. And because of this, you need to use a turbulence model so that you capture the effects of turbulence and you can get away by using a larger grid. So let's talk about turbulence modeling approaches in CONVERGE. So in CONVERGE, you have two types of turbulence modeling. One is RANS and the other one is LES. So in this particular course, we are going to be focusing only on the RANS turbulence modeling. We will not be talking about LES, other than mentioning that LES stands for large eddy simulation. Okay, so the approach that we are focused on is called as Reynolds average Navier-Stokes. So this is the approach which still people prefer for engineering simulations. LES, which typically tends to be more accurate, is still a research tool. Though companies are moving into LES-based engineering solutions, still, if you look at most of the companies that do R&D, especially with respect to flow analysis, they use a RANS-based solver. So the idea with RANS is you solve equations for an ensemble averaged velocity field or a time averaged velocity field and the magnitude of turbulent fluctuations. Right, so this might be a bit complex at this stage, but I think in the next slide we have an equation. So in the RANS modeling, the first thing that you do is you do something called as Reynolds decomposition. So the idea is this is your instantaneous field, right? So this is the accurate velocity field that you have, and what you're doing is you're decomposing that into a mean field and a fluctuating component. All right, so this mean field is what you are going to be solving for, and this fluctuating component is what you are going to be modeling. Modeling as in you're trying to approximate it. All right. So now if you take this decomposition, plug it into the Navier-Stokes equation, and if you go through some operations, you will actually end up with the Reynolds average Navier-Stokes equation. Now any standard turbulence textbook will have this derivation if you're interested in learning more about this. So at the end of the day, when you do the substitution, you will actually end up with an additional term which is called as the Reynolds stress tensor. Okay, so this is how it looks like. And the whole problem of turbulence modeling suddenly boils down to how you can calculate this Reynolds stress tensor accurately. All right, and there are several methods, and one of the most commonly used method is using a viscosity based model. The idea is, since it's a stress, what you can do is you can say that it has this viscosity term and then it has the velocity gradients. Now this right here, mu t, is what you call as your turbulence viscosity. So what you're saying is that your Reynolds shear stress is a function of this turbulent viscosity multiplied by the velocity gradients. All right, so getting this mu t, right, now all of a sudden turbulence modeling is all about how you calculate this turbulence viscosity, and for that several models are present. So with respect to CONVERGE, you have your standard K epsilon, RNG K epsilon, rapid distortion RNG K epsilon, realizable K epsilon, standard K omega, and variants of it. Now for IC engine simulations, we recommend that RNG K epsilon needs to be used, and this is more from experience and by validating a lot of cases with experimental data. So here's a general reference slide which you can use. So as I said, for RNG K epsilon, it's quite applicable for IC engine case because a lot of validation case has already been done with CONVERGE. Now if you look at K omega SST, so if you look at standard K epsilon model, we typically don't use it. Though it's actually robust and it has good convergence rate, it performs poorly in adverse pressure gradient, right? And whenever there is separation, it doesn't do very well. And these type of flows exist in IC engines and also gas turbines. So using standard K epsilon is a bad choice. With respect to rapid distortion K epsilon, it is used for IC engines, but the problem is it does not have a lot of validation data. So this is something that we typically won't recommend. Go with RNG K epsilon if you're interested in simulating IC engines. And similarly, your K omega models, right? Your K omega models are great if you're doing gas turbine simulations. And there is more explanation here. And if you're interested in some other types of flows, you can always refer to this table and pick up the best model that you can use. And one of the things with turbulence modeling is that you will end up with a lot of constants. Now these constants have been tuned to give good results for IC engine simulations. Now one of the things that you should not do is change these constants because, like I said, these constants have been carefully calibrated. And if you want to change them, you have to change them based upon, say, some kind of a reference paper where they have basically chosen a set of constants for a particular application after thorough analysis. Now one of the things that's interesting about RANS modeling is the near wall treatment. In turbulent flows, the velocity adjacent to the walls changes very rapidly. And to understand these changes better, what people do is they use a transformation. They basically convert your flow field variables into what you call as the near wall variables. So you have something called as U plus, which is the non-dimensional velocity, and Y plus, which is the non-dimensional wall distance, and U star, which is basically the friction velocity. All right. So when you plot U plus and Y plus, you actually get what you call as the law of the wall, right? So basically what you can see is that away from the wall, there are three distinct regions which have been clearly marked. The region that's closest to the wall is called as the viscous sublayer, and the region outside of the viscous sublayer is called as the buffer layer, and even outside the buffer layer you have something called as the log law layer. So in the viscous sublayer, what happens is that your viscous stress term dominates. All right, and in the buffer region you have this transition taking place, whereas in the log law region, you have your Reynolds shear stress that dominates. In other words, inside the viscous sublayer, your molecular viscosity, your mu molecular viscosity dominates, whereas in the log law region, you have your mu turbulence viscosity that dominates. So why is it important to understand this plot? Well, depending upon your turbulence model, the location of the first cell needs to be placed accordingly. Now, if you're using standard K epsilon model, it's what you call as high Reynolds number model, which means it cannot have its first cell in the viscous sublayer. In other words, if you're simulating a turbulent flow problem, and if you refine the mesh near the wall too much, such that the y plus is less than 1, then using the standard K epsilon turbulence model is wrong. If you are using the standard K epsilon model, which is a high Reynolds number model, you need to make sure that your y plus is in the log law region. Okay, so which means your y plus should at least be greater than 30. Alright, so this is an important takeaway. If you want to go up to y plus less than 1 or in that range, you need to use an appropriate low Reynolds number turbulence model, which is supported by the K omega class of turbulence models. For example, here is the table that gives you a recommendation of what type of models you need to use. So if you are using the law of the wall model, make sure that your y plus is between 30 and 100. Alright, and especially this is true if you're using K epsilon or if you're using K omega turbulence model with the log law. And similarly, there is another type of wall treatment called as automatic wall treatment function. So here the idea is, depending upon your y plus value, the code is automatically going to adjust the equations, but this is available only for K omega, right? Now K epsilon does not have it because K epsilon is strictly a high Reynolds number model. Okay, now similarly you have low Reynolds number model, which is the K omega SST model. In this case, you can actually use y plus less than 1. And this is going to give you accurate wall quantities if that is something that you desire. Now, this is one of the things that people choose when they do external flow simulations. Alright, so with that, I would like to conclude this lecture on turbulence modeling, and I'll see you guys in the next video. Bye.